So what he did was he went back to the store and he got a box that was 3 feet by 4 feet. He stuck the fishing rod in the box diagonally and brought the fishing rod onto the box.
Wait, what?
It's so simple though at the same time, isn't it?
You put that in the seat? That's the box.
This is the package that you got.
The package that you got.
So he's obeying the rules now.
Oh wow, just simple.
So Pythagorean theorem tells us we have one Pythagorean triangle, 3, 4, 5 right triangle.
You put it in the box. Yeah, and the pizza.
That's why it says Carolina.
No Carolina. Okay, so analytic tree. This is where we left off yesterday. Chapter 6. So to kind of blend in, I may have repeated myself here, but that's okay. So the 3 groups that you are now pretty familiar with are the reciprocal identities, quotient identities, and Pythagorean identities. You should definitely get your notebook out and start taking notes. You should also have your reference sheet out. I don't have any more right now, but you should have your reference sheet out. So these 3 I think you're pretty familiar with, but to quickly review, we know reciprocals, sine and cosecant are reciprocals of each other, cosine and secant are reciprocals of each other, and tangent and cotangent are reciprocals of one another. Quotient identities, tan of x is equal to sine of x over cosine x, cotan x equals cosine x over sine of x. The Pythagorean identities, I think the one that's most commonly known is the first one. Sine squared x plus cosine squared x equals 1. I did show you guys a few months ago, let's say, how to derive these other 2. So if I were to divide each side of this equation by the sine squared x, I would have 1 plus tan squared x equals secant squared x. Pardon me, I would have, this one. If I divide each side by cosine squared x, each side squared by cosine squared x, I would have this one. Thank you.
What's new? Is that bottom line or
so the ones that are the most recent that we haven't really gone over in depth are the last section here. We have the even odd identities. Notice that these 4, sine, cosecant, tangent, and cotangent, these 4 are the ones that are odd, such that the sine of negative x is equal to negative sine of x, and so forth. Cosecant negative x equals negative cosecant of x. The 2 that are even are these 2. Does anyone remember what an even function is? How it's defined? I don't expect you to. Even function is, say, we look at cosine. This is the graph of cosine. If we were to reflect this about the y-axis, meaning just flip it like this, horizontally, you would have the exact same image. That's why cosine of negative x equals cosine of x. If I pick some value, say, let's say 1/3 pi radians, which say is about right here, well, cosine of negative 1/3 pi radians is going to have the same output as positive 1/3 pi radians. And you see that would be consistent throughout. So that's why this is the way it is. Secant of x as a graph is also going to have the same situation, which is, of course, that's just its reciprocal. So it's going to look like this. So you can imagine if I were to reflect this about the y-axis, it's an even function. You can see it had the exact same image. So these are the two even functions. And then these here, these four here, these two and these two, these would be your odd functions. Another way you can remember these is eventually you want to get to the point where you can just kind of have these off the top of your head. That's ideal, especially when you move on to your next math class down the road. To state that, anyone tell me which ones are positive in the first quadrant of this case? You want to tell me which ones are positive in the first quadrant of the 6 trig functions? They all are. All are positive in the first quadrant. Anyone remember which ones are positive in the second quadrant? If you forgot, one that's easy to remember is there are 2 that stand out in terms of their period compared to the other 4. There's 2 that only have a period of pi. What are those 2? Thank you. Tangent, and of course it's reciprocal cotangent. And then filling out the rest, this is sine, and it's reciprocal, which is cosecant. And then in the fourth quadrant, cosine and secant are positive. If you look at here, the cosine of negative x. The cosine of negative 45, according to this identity, is the same thing as cosine of positive 45. Let's see if that's true. The cosine of negative 45, is that going to be a positive or negative value? The cosine of negative 45, is that going to be a positive or negative value? It's going to be positive. If cosine is positive in the fourth quadrant, it terminates in the fourth quadrant. So the cosine of positive 45, is that going to be a positive or negative value? It's be positive because they're all positive in the first quadrant. And you continue that, and of course they're going to have the same value because the reference angle is the same. If we go cosine of negative 100 degrees, it's going to be negative because only tangent and cotangent are positive in the third quadrant. If I go cosine of positive 100 degrees, it's also negative. And you continue this pattern and you would see that, oh, okay, I see why this is true. So I'm just showing you different ways maybe something will stick. It's also worth noting, just to review, even and odd functions. Odd functions are symmetrical about the origin. What that means is if I take a function and I flip it vertically and then flip it horizontally, I would have the same exact function where I started. So if you visualize something like sine. If I took this guy and I flipped it this way and then flipped it this way, I would have the exact same function. So imagine you visualize you taking this, flipping it this way. So now it would look like that. And then flip it this way, you would start. Go right back to where you started. So that's to see something symmetrical about the origin. That's what makes these odd functions, sine, cosecant, tangent, cotangent. But anyway, the big thing that you need to know is which are which. And the way you can remember them is that cosine and secant are in the fourth quadrant here. Those are the ones that are going to be the even functions, where the cosine of negative x is simply cosine of x. The other ones produce the opposite. If I take the sine of the opposite of any given input, it would be the opposite value if I took the opposite value of that input. Anywhere, in other words, sine of negative x equals negative sine of x, and so forth. Okay. Study tip I think is important is to memorize the identities in the box. Eventually start to memorize these. I know these two are probably going to be the toughest, but you will have the reference sheet available to you for all quizzes and tests in this class. So you do have that, but it does help to at least recognize, oh, I know I'm going to be using this when you see what I'm talking about when we're solving these puzzles. If you like solving puzzles, you might like this section, this chapter, more so than others, especially if you also don't like graphing, because there's no graphing involved. Here's the identity that we're I think all pretty comfortable with. Sine squared x plus cosine squared x equals 1. just know that you could either use alterations of it, alternative versions of it. Sine squared x equals 1 minus cosine squared x, and so forth. So, there's a couple of things I need to make emphasize here. And I think I mentioned this Friday, but I'll mention it again. Each side of the equation is manipulated independently of the other side of the equation. So we're not doing like when we went to say solve for a variable like this, where you say, oh, I'm going to minus 6 on each side, and then divide each side by 3, and I solve for x. That's not what we're doing here. What we're going to be doing is we're basically going to be doing what are like proofs. If you remember doing proofs for geometry, right, you had to prove that this angle was converted to this angle, and you had to go through so many steps. And say, okay, we have angle, symmetry, or and then we have side angle, side congruency, whatever it is, SAS congruency. Then we have vertical angles are congruent by whatever theorem postulate states that, and then the sum of all the angles, this angle plus single is 180 degrees because the sum of the interior angles of a triangle is 180 degrees. Same kind of idea. These are like going to be like proofs. So you work on each side independent. I had a student ask in one of my periods, why do we do this? And it's a good question. The difference between what we're going to be doing in this section and what we've done, like when you, let's say, back in algebra where you solve something like this, the difference is this. This is when you're given the problem like this, up here in purple, where it says 3x plus 6 equals -1. We are already under the assumption that this is a true statement. We're just solving for x. So because it's a true statement, we say, okay, we can minus 6 on each side, that'll keep it balanced. We can divide each side by 3, and we'll solve for x. This is not the case here. In this case, we don't know necessarily if what we're given is true. We're going to verify to see if it's true. That's why we have to obey this rule here. Another big thing is if you substitute one or more fundamental identities on the more complicated side, you will often be able to rewrite it in a form identical to that of the other side. So we really want to work on the side that's more complicated. It makes no sense to take something that's very simple and make it more complicated. We're going to simplify something that's more complicated and make it look like the right-hand side or vice versa. No one method or technique can be used to verify every identity, so you may use different techniques, different methods. Some identities can be verified by rewriting the more complicated side so that it contains only sines and cosines, and that's what we'll be doing for the first few of these. You don't have to write this whole thing in your notes, but maybe if you want to emphasize in your notes that you work on each side independent of the other. I doubt you're taking notes on your phone. Thank you. So that being said, couple other points. Need more time?
Yeah.
Okay. You don't have to worry about writing the whole thing. I would just emphasize that, yeah, each side, work on each side individually. And probably work on the more complicated side first. Try to simplify the more complicated side.
We work on the harder side first.
Yeah, work on the more complicated side first. You may also want to write that it's useful to substitute values so that you get it in terms of sine and cosine. We're going to see some examples. We need more time. Don't be afraid to stop and start over again if you are not getting anywhere. This can happen when doing these. Let's say you're looking down the line, and all of a sudden it's just getting more complicated. Nothing seems to be going anywhere. You may start all the way over. You may go back a few lines and say, well, you know what? This line here, this looked pretty good. I look pretty good here, so I may go back to here. Because it started getting really nasty after that. Maybe I was doing some, maybe I should try here. Or maybe I do have to go all the way back. Nothing wrong with starting over. And another thing I want to point out is to try something. If you just stare at these and don't write anything down, don't try, you're never going to see it. Example 1. Verify the identity. Secant x times cotangent x equals cosecant x. And they're already kind of leading you, telling you what to do. They say changing to sines and cosines to verify an identity. So we'll go down that path and see what happens. For right now, I want to do step by step. Some of you may feel comfortable substituting values in from identities all in one step, but we'll go ahead and do step by step. Yes?
Are they multiple?
Yeah, secant of x times the cotangent of x equals cosecant of x, yeah. So I'll do this one. You guys can follow along. Anyone have any idea? I mean, changing to sine and cosine? There's more than one way to start this. There's not necessarily one specific way. But if we just say, let's just work on the left-hand side. Let's see what we can get. So what's one thing we can do? Divide, you say? Divide what? So you have your reference sheet out in front of you, you see, look at your reference sheet, and you're looking to, you know that it's being hinted at, okay, if I change things to sine and cosine, I might be able to get to where I want to go. So there's something we can change.
The sec to cosine?
So secant of x is what? If you're looking at the reciprocal identities, secant of x is what? 1 over cosine of x, yeah. So secant of x is 1 over cosine of x. I'm going to leave the... Anytime you see just equals, it's assumed that the right-hand side has not changed. And so your justification for the step is simply you just write reciprocal identity.
So that question.
Yes.
How about on this paper, on our reference paper, it uses u instead of x. Does that matter? Okay.
Just a variable.
All right.
Okay, so next step.
Is parity identity?
I wouldn't do that because I don't see anything else in here that has negative x as the argument. So, and I'm saying, again, just work on the left-hand side because the right-hand side, we all agree, is very simple. It's just cosecant x. Yes? What do you mean do the same? What do you mean? Cotangent of x is not equal to sine of x over cosine of x. Cotangent of x is equal to 1 over tangent of x, but I'm telling you that we really want to get everything in terms of sine and cosine. Yes? Because I want to get everything in terms of sine and cosine, and I know that the secant of x is equal to 1 over cosine of x, according to my reciprocal identities. Yes? Cosecant of x is 1 over sine of x, and we can do that.
Is it better to leave it like that?
Again, it doesn't matter. We can do that. I'm just saying, just for this particular problem, let's just see if we can just work on one side and see what happens. There's nothing wrong with doing that. Kind of like pushing you, there's only one thing to work with here. Is there a way to write cotangent of x in terms of sine and cosine? Yes. Yes, cotangent of x is cosine of x over sine of x. Good. Good. And so clearly we can see that this does simplify to 1 and 1. So we are left with 1 over the sine of x. And the justification for this step was simply, what was the justification for this step? What was identity we're going to do? And the justification for this step was what? Multiplication? You could put simplify. We're almost there. We're at the very end. 1 over sine of x. We know that actually is cosecant of x. So cosecant of x equals, we can now bring it down to show
That means it's right.
that we have verified it. So this identity is true, we verified it. And so this, again, the justification for this stuff is the reciprocal identity.
Hey, Mr. Burke,
Yes.
what did you do with the 1 over sine?
What I do with the 1 over sine, it's just there. If I go straight across, 1 times 1 is 1, 1 times sine of x is sine of x.
Oh. So the goal is to make it equal whatever is on.
Yeah, the goal is to get the left-hand side to equal the right, match the right-hand side, exactly, yeah. We could just say simplify here, I'm fine with that. Simplify or multiplication, whatever. And then so now we've reached the end. All right, they both sides match, we're done. So this identity is true. We have verified it by using our identities. Yes?
Some of them will be true. Or they'll always be true.
I'm only going to give you ones that are always true. You just have to show how you verify it. Any questions? Yes.
How did you, okay, so after you got the 1 over cosine of x, equals cotangent of x, how did you get the,
Stop. 1 over cosine of x equals cotangent of x?
I meant times cotangent of x.
Oh, yeah.
1 over cosine of x times cosine of x over sine, how did you get that?
If you look at your reference sheet, under quotient identities, it says that cotangent of x is equal to cosine of x over sine of x.
Okay. But,
And then when you do that, you notice, oh, okay, this is nice because this makes it more simple. Cosine of x over cosine of x is just 1. So I have here, I write here.
okay, so then how did you get cosecant of, wait,
Reciprocal identities tells us that 1 over sine of x is cosecant of x.
oh, okay,
Good?
yeah.
Anyone need more time? Any questions?
Now I'm gonna do another one.
Example 2. I don't know why this one is so small.
Can I do it on the board?
You can if you want, sure, yeah, go ahead.
I have to look at her. I have to write it down.
Yep, we're going to do another one right now. So, changing to sines and cosines to verify identity is the same basic process. The general idea, let's change stuff to be in terms of sines and cosines. First off, let's all understand this. The right-hand side is much more simple than the left-hand side. The right-hand side is just one single term, secant of x. The left-hand side is 2 terms, and the first term is a product of sine of x and tangent of x, and the other term on the left-hand side is cosine of x. So the left-hand side, we all agree, is more complicated than the right-hand side. So let's go with what we're learning. Changing things to be in terms of sine and cosine. I'm going to watch.
Are you kind of like guessing and doing, trying different things and changing?
Almost. It's like solving puzzles. You have to kind of try something to see if it works. As long as you obey the rules, then you're fine. There is more to do these, yes.
Tangent, you can make sine of a cosine.
Yep. Let's go ahead and do that. So sine of x times, we're making tangent sine of x over cosine of x. One thing you notice about the left-hand side versus the right-hand side is, like I said, the left-hand side is 2 terms. The right-hand side is just one single term. So we're probably going to move down the pathway of combining these somehow. If they don't combine well, we're going to have to combine them. So this was done by, this is a quotient identity.
Wait, so I started off wrong already.
Again, it's not necessarily true. There's more than one way to do these.
Okay.
I'm not sure if I want to go down your pathway because it's typically easier when we have it written in terms of sine and cosine. Yes, Evan.
So in your reciprocal identities, couldn't cosine of x be turned into just secant? Reciprocal identities, cosine of x.
Okay, so again, we want to change everything to sine and cosine. Let's do that first. And we'll just work on the left-hand side right now, because the right-hand side, again, is very simple. We're going to leave the right-hand side alone. Anyone have an idea of what we do next? What do you think we might do next? Have we converted everything on the left-hand side to be in terms of sine and cosine?
Yeah.
Okay, so why don't we go ahead and simplify the left-hand side? Yes.
Okay, so I times the two signs, I pretty much did like the top, so I times the two signs with the sine squared.
Okay, so she's multiplying this with this, is what you're trying to say. Yeah, and what would you get?
I got sine squared plus cosine over cosine of x, and then I use the Pythagorean.
No, stop. So sine of x times sine of x is not what you just said. No, sine of x times sine of x is just sine squared x.
Yeah, that's what.
Okay? All over 1 times the cosine of x is just cosine of x.
I can see where this is really stressful.
Okay? Well, when you're not participating at all, I can understand as well. Alright, so we have this on the left-hand side. Is there any way to combine these as to one expression? Let's think. What did we learn years ago? Example. 1/3 plus 2/7. How do we combine these?
Turn it into the same denominator.
Same denominator. Okay, what's the least common denominator? 21. So something 21st plus something 21st, okay? 7 21st plus 6 21st is going to be 13 21st. So let's try to combine these two.
You multiply the bottom by cosine.
The bottom. Yeah, I'm not doing
You
it.
put cosine equal to 1.
Okay, good.
And you multiply 1 by cosine. You talking about
Very good. Top and bottom by cosine x. So we would have sine squared x over the cosine of x plus the cosine squared of x over cosine of x is equal to the right-hand side. Good. And so the justification for this one, simplify, multiply. You can put multiply fractions.
you gotta write that aside.
Multiplication, yeah, justification, that's good. And then LCD, I'm fine with that. Least common denominator is cosine of x of these two fractions. And then we put them together. So we put this together as one, now we can. So it's sine squared x plus the cosine squared x all over the cosine of x is equal to the right-hand side. This is just addition of fractions. You just write addition, that's fine too. This is where you should have an aha moment and know that sine squared of x plus cosine squared of x is just 1. So you have 1 over the cosine of x is equal to the right-hand side.
Wait, how did you know? Because that's the form.
That's a Pythagorean identity. Those guys.
1 over
You just
cosine.
thought it's 11. Oh, them right there? What does that say? This is I did multiplication.
And so 1 over cosine, what's that?
What is that?
Multiplication LCD, add addition of fractions, Pythagorean identities, and then finally 1 over cosine of x we know is the secant of x, so we can just go ahead and write that. Secant of x equals the secant of x, so we're done. And this is justified by reciprocal identities.
You can tell it better.
In the LCD stuff, where you have the cosine squared x over cosine x. All you do is multiply. To go from the multiplier to the LCD stuff, you just multiply top and bottom by cosine x.
Yep.
And then you just combine like 10 to sine squared x plus cosine squared x over cosine x. Okay, that's what I was trying to do.
Questions about this one?
Right there on the LCD is what? Is all what?
Addition of fractions.
Oh.
I'm fine with the right and simplify as well, that's fine. Yes. Sure. Just multiplication. Sine of x times the sine of x over cosine x. Uh-huh.
What is it like over LCD says?
Multiplication. These get a lot worse. So if you're not taking notes, shame on you. When you're going through the mind field, it is the quiz or test on this, and you come up to me and ask for a hint, I will say nothing.
Refer to notes.
Yeah. It's an open no test.
You got this.
Okay. Example 3, using factoring to verify an identity. So the example is already pointing you in the correct direction. It's telling you what you should be doing. You should probably be factoring. But let's say you didn't know this. I know it's kind of obvious because now it's been stated out loud. But let's say it just says verify the identity, and it says cosine of x minus cosine x sine squared x equals cosine cube x. We would all agree and hope that the right-hand side, again, is more simple than the left-hand side. So we're going to leave the right-hand side alone. At some point, we're probably going to combine to get a single expression on the left-hand side, or a single term, because the right-hand side is just cosine cube x. It's a single term. But we look at this, and we really have no way of combining these, do we? There's no way to, how do you combine cosine of x and negative cosine sine squared x? That's like, okay, how do you combine x and then negative 3xy? Well, we can't. So the only other thing that you do have is factoring. So let's see what happens. Because again, a lot of times you're not going to know what to do. You're just trying things. Yes, a question?
Can I subtract that or no?
Could you subtract what?
Cosine of x minus cosine of x instead of like this.
Well, this term is not just cosine of x. It's cosine of x sine squared of x. It's like asking me this, if you could subtract these. X minus xy.
I would have to divide.
You have to do what?
I would have to divide.
Divide what?
Both sides of x. Like, wouldn't you divide the x?
Factor out or divide?
Yeah, sure. Factor out.
Okay, because if I divide, let's say, the whole left-hand side by cosine of x, wouldn't I also have to divide the right-hand side by cosine of x?
Yeah.
Are we allowed to do that? Right, we can't because we're verifying the identity. So what we can do is we can factor out, if you notice these both have cosine x in common. So if we factor out cosine of x, what would we be left with, Amaris?
Sine. 1.
Good.
Sine. Sin. Minus.
1.
Question. Cosine of x times 1 is cosine of x. Cosine of x times sine squared of x is
Why
cosine
did
of
you
x
put
sine
this
squared of x.
minus in front of that? In front of the 1 and not.
Because you never got rid of it, it's still there. You just factor out the cosine.
Wait, what? In fact, the sign is not negative, it's the other one.
No, listen,
Negative cosine.
when you factored out the cosine of x, you just took out the cosine of x, you didn't get rid of the negative, it's still there.
If you factored out a negative cosine x, it would take the negative away.
Yeah, well, we did, we're just factoring out positive.
Okay, so does anyone recognize this? What? Sure.
It looks like I recognize it, but I don't know.
Okay, look at your Pythagorean identity.
Go to school like that tomorrow.
Wait, how'd you get from
Pythagorean identity that states that sine squared of x plus cosine squared of x equals 1.
where's
That's the Pythagorean identity.
Oh, I see. I would not have known.
There's a longer way to do it, but I'm fine with you guys going straight from here to here. If we go back to the beginning of the lesson, I did state it was a good idea to be able to recognize if sine squared of x plus cosine squared of x equals 1, then sine squared of x equals 1 minus cosine squared of x, and cosine squared of x equals 1 minus sine squared of x. Yes.
How did you get from down to that?
To this from here to here,
Yes.
Pythagorean identity. Oh, yeah, Pythagorean identity. If you had to reference it out like you're supposed to, you can see under Pythagorean identities that sine squared of x plus cosine squared of x equals 1. So 1 minus sine squared of x is cosine squared of x.
Can you slow down real quick? You said that. What?
Underneath Pythagorean identities, it says sine squared of x plus cosine squared of x equals 1. Therefore, 1 minus sine squared of x is cosine squared of x.
Sine squared plus.
I can show you the long way if it makes it any more clear, although you guys are probably not going to like it.
No.
Wait.
So you still can't. So some of you still can't see it. At least one of you still can't see it. So I'm going to show it to you. According to Pythagorean identity, 1 is equal to the sine squared of x plus cosine squared of x. So I'm going to substitute that for 1. This is justified by the Pythagorean identity. And if you want to really see step by step, I'm allowed to, according to the commutative property of addition, I'm allowed to move things around. This is the commutative property of addition. This is 0.
Mr. Gross, can you go back to that another picture when you're done? Just to underline, this is what I did here. I replaced 1 with sine squared x plus cosine squared x. You want me to go back to this picture here? Yeah, it's really annoying and rude.
You guys jabbering. Yeah.
You're using your government?
Yes. Yeah.
Why in the third line, why did you use
So I could max these up so that that's 0.
oh,
The commutative property of addition says that order of addition doesn't matter.
Oh, I got you now. See, now you explain it better.
Yeah, I did it just for you.
Right. I got you. Yeah, that's
Anyone else have any questions about this one? Looking at another one. Using 2 techniques to verify an identity. Method 1, separating a single term quotient into 2 terms, and then different method, changing to sines and cosines. So I'm going to show you both. This is really just to demonstrate that you can do these more than one way. I don't want you guys to feel like there's only one way to do these. There's more than one way to do these.
Does that say sine of 0 or sine of theta?
It's 1 plus sine theta over cosine theta equals secant theta plus tan theta.
Thank you.
So the given is this. It says method 1, they're telling you to give you a hint that it's separating a single term quotient into 2 terms. So if we separate this into 2 terms, we have 1 over the cosine of theta plus the sine of theta over the cosine of theta. We're allowed to do that. Equals the right hand side. And now, if you look at the right-hand side, you say, wait a second, I know that 1 over cosine of theta, that is secant of theta, so that's going to be worth changing to that. And I recognize the sine theta over cosine theta, that is tangent theta, so I'm pretty much done here. If I do one at a time, I'll say secant of theta plus sine of theta over cosine of theta is equal to the right-hand side. And finally, this here is a quotient identity. And the justifications for these, first one was just this. That's what went on here. Here, we had reciprocal identity. And here we just had quotient identity.
Is the last one the answer? Or do we have to put it back on?
The answer,
Or
we verified the identity, so we're done. And changing to sines and cosines, we're low on time. If I leave the left-hand side alone, if I change secant to terms of sine or cosine, secant is the reciprocal of cosine. And tangent is the quotient identity we have for that is sine of theta over cosine of theta. We can combine these two and have 1 plus the sine of theta over the cosine of theta. And we're done. I combined 2 steps into one here. Reciprocal identity and here quotient identity.
Can you move your head, please? It is a little bit.
Mars.
Yeah.
You gotta put it back.
can I have my phone?
We got 18. And one right now. Why are you always out?
Sounds good.
Sounds good.